Hey everyone, welcome to today's Explainer. I'm super excited to have you here because we're going to demystify something that's honestly one of the most powerful tools in industrial chemistry, but also one of its absolute biggest threats. We're talking about the anatomy and the defeat of industrial fire. So whether you're an engineering student, maybe a chemistry major, or honestly just someone who wants to know the hidden science keeping your campus safe, you are definitely in the right place. So let's just start with this. How exactly do you stop a fire that doesn't even need a flame to start? We usually think of fire as needing a match or a spark, right? But if you look at Class F fires, these are the ones involving cooking fats and oils, they can reach auto-ignition at 340 degrees Celsius. Literally, at that temperature, the oil just bursts into flames all on its own. Absolutely no spark required. And that right there is the kind of extreme chemistry that safety engineers are battling every single day. Okay, let's dive into this. Here's our roadmap for the explainer. 1. The anatomy of a fire. 2. 6 classes of industrial fires. 3. Stopping fires with active defense systems. 4. Built to survive with passive fireproofing. And finally, number 5, managing and assessing fire risks. All right, kicking things off with section 1, the anatomy of a fire, breaking down combustion. Let's take that familiar concept of a campfire and really scale it up to massive industrial chemistry. At its absolute core, fire is just a chemical reaction. Specifically, we're talking about combustion, which is the rapid oxidation of a material in an exothermic process. And exothermic is just a fancy way of saying it releases energy, and I mean a ton of it. The conversion of the weak double bond in molecular oxygen to the much stronger bonds in carbon dioxide and water releases 418 kilojoules of energy for every 32 grams of oxygen. That's staggering release of heat and light. That's the fundamental enemy we're trying to control here. Now, you've probably seen the classic fire triangle in a basic science class at some point. It shows that fire needs heat, fuel, and oxygen. But I want you to pay attention to the green base of the triangle, a self-sustaining chemical chain reaction. If you want to defeat a fire, your entire engineering strategy really boils down to removing just one of these 4 things. So remove the oxygen, cool the heat, starve the fuel, or interrupt that chemical chain reaction, and the fire literally dies. What's really fascinating about this is how extreme heat actually transforms the physical state of matter. We start with solids or liquids, which then evaporate into a gas. That visible flame you're used to seeing, that's actually a mixture of carbon dioxide, water vapor, oxygen, and nitrogen gases. But if you keep adding energy and the fire gets hot enough, those gases can actually become ionized. The electrons literally get stripped away and the gas transforms into plasma. That, my friends, is industrial-level heat. Moving right along to section 2, 6 classes of industrial fires. Categorizing the threat, because you can't fight an enemy you don't understand, and using the wrong weapon can make a fire infinitely worse. So engineers categorize fires into 6 main classes, and it's all based on their fuel source. Class A is your everyday solids, paper, wood, basically the stuff sitting in your dorm room. Class B involves flammable liquids like solvents and fuels. Class C is gases. Class D covers highly flammable metals, think magnesium or lithium. Then we have electrical fires, and lastly, Class F, which is those cooking fats and oils we talked about earlier. You absolutely have to know exactly which class you're dealing with. To give you an idea of why those classifications are so crucial, let's contrast a couple of distinct hazards. On one side, we have an electrical hazard, and on the other, a super volatile Class F cooking oil fire in a commercial kitchen. If you've just got a simple Class A paper fire, a standard water extinguisher is perfect. But spray water on a live electrical box? Yeah, you just became a conductor. Or spray water into 340-degree auto-ignited cooking oil. The water instantly turns to steam, expands rapidly, and creates this massive fireball. You need entirely different chemistry, like wet chemical extinguishers utilizing potassium salts to safely smother that oil. And speaking of electrical hazards, this one is incredibly relevant to all of us as students. Did you know that over 60% of fires are actually of electrical origin? They happen because of super common things: faulty wiring, overloaded breaker boxes, daisy-chained extension cords. The precautions are simple but absolutely critical. Use certified appliances, replace broken plugs, and never ever overload a single socket. These are the exact kinds of hazards that are just lurking right behind the drywall of any older campus building. All right, Section 3, stopping fires with active defense systems. When a fire actually breaks out, this is the physical arsenal that's designed to fight back. Let's walk through the life cycle of a sprinkler head. You know how in Hollywood movies someone pulls a fire alarm and suddenly every single sprinkler in the entire building goes off at once, soaking everything? Yeah, totally a myth. Sprinklers are actually brilliant, highly localized little machines. Under normal conditions, the system is fully pressurized. When a fire breaks out, the ambient temperature rises directly around the localized heat source. That's what triggers the activation. Water begins to flow, and you get targeted fire control right where the flames actually are. It conserves water and totally saves the rest of the building. And this brilliantly illustrates how it works. Take a close look at the glass bulb holding that pipe cap in place. That little bulb is actually filled with a heat-sensitive liquid. As the heat rises, the liquid inside expands. Once it hits its exact, precise design activation temperature, the glass shatters. That drops the pipe cap plug, and bam! The pressurized water bursts out through the deflector. It's a completely mechanical and incredibly reliable failsafe. But engineers don't just rely on basic water pipes, right? They build highly specialized defense arrays. There are actually 8 specific types of sprinkler systems depending on the exact hazard. A wet pipe system is your standard go-to. But what if those pipes are outdoors in freezing temperatures? You'd use a dry pipe system filled with pressurized air instead. Trying to protect an industrial liquid fuel fire? You're going to want a foam water system that mixes in foam concentrate to blanket the fuel surface and suppress those dangerous vapors. Every single system is tailored to the exact chemistry of the threat. And that same targeted engineering goes right into a portable fire extinguisher. Inside that heavy metal cylinder, there's a siphon tube running down into the suppressive agent, which, by the way, could be powder, foam, or a wet chemical. When you pull the safety pin and squeeze that lever, it pierces a highly pressurized CO2 cartridge. That sudden release of gas violently forces the agent down, back up through the siphon tube, out the spray nozzle, and right on to the base of the fire. Let's move on to Section 4, Built to Survive, Passive Fireproofing. Because what happens if those active systems fail, or if they just need a little more time? So the crucial point here is the fundamental difference between the two. Active fireproofing requires human intervention, like someone grabbing an extinguisher, or an automated system action, like that sprinkler head bursting. Passive fireproofing, though, that is built right into the architecture itself. It requires absolutely zero moving parts. It just sits there and impedes the spread of fire and toxic smoke purely through its structural and chemical endurance. Here's one of the biggest secrets of modern engineering. Structural I-beams, the massive steel skeletons of skyscrapers and industrial plants, actually lose their load-bearing strength incredibly quickly as temperatures rise in a fire. To stop a building from totally collapsing, engineers rely on passive protection methods like concrete or brick masonry encasement. By literally wrapping the steel in concrete, they dramatically delay the metal's exposure to those extreme high temperatures. And that buys people the time they need to evacuate. Now, our concrete is just too heavy. They turn to some really high-tech coatings. You can spray structural girders with cementitious plaster to keep the steel safely below 540 degrees Celsius. But what's truly mind-blowing to me is intumescent paint. You paint it onto metallic pipes and valves in this super thin layer, but when it gets exposed to extreme heat, it undergoes a chemical reaction and rapidly expands into a thick, charred insulating layer. It literally grows a thermal shield right exactly when it's needed most. How cool is that? All right, our final structural point, Section 5, Managing and Assessing Fire Risks. Because the absolute best way to fight an industrial fire is to make sure it never even has the chance to start. For all you students heading into engineering or management, you need to know that fire safety is a highly rigorous, intensely data-driven discipline. Facilities use advanced risk management frameworks to assess every possible hazard. They use cause and effect, also known as Ishikawa, diagrams to trace root causes. They run failure mode effects analysis, or FMEA, to predict literally every single way a component could break. They build fault tree analyses to map out the cascading effects of a localized failure. It's essentially a kind of highly organized, proactive paranoia, and it saves thousands of lives. And all of this rigorous planning translates directly into visual cues in your environment. Take a look at the NFPA 704 standard, widely known as the fire diamond. You've definitely seen this on the doors of chemistry labs or on industrial tanks around campus. Emergency personnel use this to instantly identify hazards on a scale from 0 to 4. The blue diamond is the health hazard, red is flashpoint and fire hazard, yellow is instability, and white denotes specific hazards like corrosive or radioactive materials. It's an immediate, universal language of risk. Which brings us to a really powerful mantra from our source material: planning today, safety tomorrow. Every single sprinkler bulb, every layer of that intumescent paint, and every complex fault tree analysis is built entirely on the philosophy that rigorous planning today is literally the only way to guarantee safety tomorrow. We aren't just reacting to fire, we're actively engineering environments where it's starved of the opportunity to thrive. So as we wrap up this explainer, I really want to leave you with a bit of a challenge. Knowing the incredible, invisible engineering required to categorize, fight, and survive just a single spark, take a look around the room or the building you're sitting in right now. Where are the sprinkler heads?